So what we would like to discuss today is what you can say about probability distributions of large sums of variables. So we want to consider several random variables and see what we can say about combinations of them, in particular sums. Say you make measurements n times, you take an average, or you look at the scatter of the data, and you want to see what you can infer about the probability distribution of these objects. So let's maybe repeat a few notions that maybe you have already seen. So first, I want to talk about probability theory of many or a large number of many variables. The final goal is to understand actually a very important theorem, which is the central limit theorem, which tells you that if you take independent random variables and you sum them up and you ask about the distribution of the sum, you will always get a Gaussian normal distribution. That's a very important theorem that appears everywhere in physics and also beyond physics. And I want to give you a feel of this theorem and how it comes about. Okay. So the first thing we'll repeat is we take two random variables, x and y. They can be discrete or continuous. And did you discuss what it means that these variables are independent? Can somebody tell me what it means to have independent variables? Can you tell me? Mm-hmm. Right. So if I know something about y, I don't know anything about x, then I call them independent. Otherwise, there's a dependency, or as we say, there's a correlation. So, and formally, this means this is equivalent to saying that the probability for x and y to take certain values is the same as the probability that x takes this value times the probability that y takes another value, and there is no interrelation between the two. And so consequences of such independence, when you have independence, then it follows that the average of the sum of these variables is equal to what? Is the sum. So I guess you have derived that, right? Or do you want to see that again, how this works? You just sum over all the possible realizations of what x and y is, and then you just see that this holds. And actually this holds independent of whether the variables are independent or not, because the sum is something so simple that this is always true. So this is even true when the variables are completely correlated. But you can also ask, for example, about the product of x times y, and ask what is the average, for example. And here, if you have independence, then again you find that this is equal to x times y. And how do you show that? Well, as I said, you have to sum over all possible realizations. The realizations of x I call xi, and the realizations of y I call yj, and I and j go over the allowed values for these variables. And here I have to put xi and yj and their probability. That's just the definition of what an expectation value is. Now, if I have independence, then this is equal to the product, right? Then I can write this as a sum over I of xi p xi, and then a sum over j yj p yj. Right. I separate this sum into two sums, and there's a product, and this is equal to x times 1. Okay. So I guess that you have already seen. Is there some? No. Okay. Now, have in mind that you, as an experimentalist, for example, you want to measure a certain observable, or you know that, that you look at the velocities of particles in the air, and you want to see what is the distribution of these velocities. By the way, does somebody know what is the distribution of velocities of particles in a gas? Maxwell, and what is the Maxwell distribution? How does it look? It's a Gaussian distribution. Okay, so suppose you don't know that, right? So, and you want to establish that. Well, maybe you don't want to find the full distribution, but you want to know the average of the velocity, and you want to know the typical, the variance or the distribution. So what do? You measure velocities one by one, and then you take a lot of measurements, and you take the average of these measurements, and you hope that this is somehow telling you the true average of the distribution, right? And now we want to understand how good are you doing if you take 100 measurements? Are you getting the average exactly or almost exactly? Or if you do 1,000 measurements, is the result going to be better by a factor of 10 or by a factor of square root of 10 or what, right? So, and in order to do that, we want to understand what happens with sums of many random variables. So think of these as the velocities of your particles that you want to measure, and I want to see what is the average. So I define a random variable as the average of n measurements of independently drawn random variables of which I would like to know the distribution, right? Or a certain characteristic of the distribution, namely I would like to understand what is the average. Okay, so I define this variable here. And the first question is, what is the expectation value of this random object? Right? Each of these things is random. So the whole thing is, of course, also random and has a distribution. So what is now the expectation value of this thing? Can you tell me if all the xi are independent variables, so each one is a different gas particle, but identically distributed. So they all come from the same distribution. So the probability that xi is equal to some x is equal to p of x, j equal to x. That is the meaning of identically distributed. So what is the expectation value of this object? Yeah, okay. So as before, we said that the expectation of a sum is the sum of expectations. Then we divide by 1 over n. The expectation of a variable divided by n is the expectation of the variable divided by n. So we have 1 over n times the expectation of x1 plus etc. plus xn, right? If they are all identically distributed, this will all be equal to the same mean of this distribution, right? So you have n times the same term here, and you just get the expectation value of the distribution. Of course, that's quite logical. Now, if you take n times independent samples of a distribution, then the expectation value of the average of that is, of course, the expectation value for each variable, right? So, so if you want to estimate the average of your distribution, this x bar, which is a property of the distribution that you want to measure, you just measure n times, you divide by n. That should be a good estimate of this object, right? But of course, it's an estimate because this is random. Good. So now if I want to ask about the variance of such a sum, so how much does this still fluctuate? That will be a bit less trivial. And so what is the variance of this object here? Have you already discussed that? Do you know what is the variance of such an object? Okay, by definition, the variance is also sometimes, I don't know, did you use this notation or sigma squared of, so this is called variance or standard error squared, error. So sigma is called standard error, or this is also called root mean square deviation. Root mean square. Okay, by definition, this is, you take the object, square it, you take the average of the square, and you subtract the square of the average. Right? And that tells you, if you take the square root of that, that gives you an idea of how much this variable that you're looking at is fluctuating around its average. No? So if you have, this is your object, which I call now bracket x, it has a certain distribution. No? So P of x, that will look something like this, maybe, right? So it has an average and it has a typical width, and this sigma, or the variance, the square root of the variance, is this typical width. Okay. Tell me if I'm going too fast, or if that was not, or if I'm going too slow also. Okay. So this is the average, and this is a typical measure of fluctuations, right? Okay, now we want to know, how does such an object fluctuate? And why is that an interesting question? Well, so this probability tells you that this object, the probability distribution, say, of your velocity distribution, has a certain width, no? And for example, for the Maxwell distribution of the velocity of gas particles, this width is more or less of the same order as the average of the velocity. So it's a pretty big scatter. So if you just take one measurement of gas particles, you will see maybe this value, you will see maybe that value, and you get a very bad estimate of the average. But if you take more and more measurements, then you expect that your average will be closer and closer to this real average, right? And how much closer it is, that we can quantify by calculating the scatter of this variable, which is the average of n measurements, right? So we want to understand what is the scatter of the average of n measurements. Good, so let's calculate now the variance of this. Okay, so for that, we first want to understand what is the variance of two variables. So just by definition, again, the variance of the sum of two variables is the the sum squared and averaged minus the average of the sum squared. Okay, now we can multiply that out. That gives x1 squared plus 2 x1 x2 average plus x2 squared average minus x1 minus 2 x1 x2 minus x2. Okay, I just multiplied these things out, and I took here the average after the multiplication and here before the multiplication, right? Okay, now I reorganize that. So I take the terms together, this and that, and then this and that. And then we have also here 2 times x1, x2 average minus x1 average, x2 average. Okay, so this you recognize by definition as the variance of x1, or sigma x1 squared, sigma squared of x1. This is variance of x2. And this here, what would you say about this term? Yes. Did you discuss correlations actually? Maybe you have seen that also. So this is a correlation term, and say just by definition, people denote that as, you can write it as sigma x1 times sigma x2 times, now by definition, rho 1, 2. So rho 1, 2 is just this thing divided by the standard errors of x1 and x2. And this rho 1, 2 here is called a correlation coefficient, I guess coefficient or correlation function. Okay, and it tells you how much x1 and x2 are not independent, right? If they are independent, then you know that, if you are independent, then you know that the average of the product is the product of the averages, and this becomes 0, no? So rho 1, 2 is 0 if x1 and x2 are independent. Okay? But in general, this is not 0. Okay, and if this value is positive, it tells you that the values of x1 and x2 tend to go into the same direction. If one deviates from the average in one direction, the other probably also does. If this coefficient is negative, you say there's anti-correlation. So when one fluctuates away from the average to the left, the other rather fluctuates to the right. So this contains some information about the mutual influence of the variables on each other. Okay. But we want to consider actually the case of independent variables over here, because we look at independent drawings, samplings from the distribution. So if x1 and x2 are independent, what we find is that this is simply the sum of the variances up here, right? Because then this term is 0. Okay, so we find the important result that if I take two independent variables, the variance of the sum is the sum of the variances. And remember that is only true if they are independent. Whereas for expectation values, if I write expectation value, then you know that this is this holds, but this holds even when the variables are dependent, actually. Whereas for the variances, this is not true. Okay, good. So now it's an easy step to go from this result by induction, you can, of course, easily show that the variance of a sum of n terms will be the sum of the n variances, no? So the variance of x1 plus x2 plus etc. will just be equal to variance of, well, sometimes I write var, sometimes v. Let's maybe just write v now, then it's easier. This follows just from induction, right? If you know it for 2, then you'd show it for 3, regarding this as one variable, and then plus x3 is the other variable, and it follows immediately. Okay, so what happens if I take the variance of the same expression, but then divided by n? Let me maybe say, so this is of course n times the variance of this variable that you're looking at, of which we want to characterize the distribution. So what happen? What is the variance of the same term divided by n? So 1 over n or 1 over n squared? Yes, true. It's 1 over n squared, but how do we see that? Well, just as a little side calculation. If you have the variance of any variable divided by some constant a, by definition, this is x over a squared minus average minus x over a average squared, and you see that this is just 1 over a squared times x squared average minus x average squared. So this is 1 over a squared b of x, right? So this will be 1 over n squared of the variance that we wrote above here, which is n times v of x, right? Okay. So the important thing is that this is the variance of the distribution, but now divided by n. Okay. So, and what is the meaning of this? This very fundamental, very simple fact that is also very intuitive, but of course you need to really have that completely internalized. So if this is my distribution of, say, the velocity of particles or something,
when you divide by n, you will not change.
I will not. Yes.
Why the first line?
Here?
Yes, you call this.
Yes.
You call n times vx.
Yes.
Okay, second line,
Mm-hmm.
you divide by n.
Yeah.
But you should also divide the second number by n.
No, so here I'm using this thing, okay? So I have some object, which here I called x, which now is this sum. And I say the variance of the sum divided by a constant a, which here is n, is 1 over this constant squared times the variance of this object. And the variance of this object was this, right? Okay. Good. So what is the physical meaning of this? So this is the probability distribution of the object that we are sampling here, no? Of one of such terms, right? It has a mean and it has a certain variance. Now what we do, we take n measurements and we take the average, and the average will, if I take 3 measurements, for example, the average will be much closer to the mean. Maybe the average is sometimes here, sometimes here, sometimes here, if I take 3 measurements. If I take 5 measurements, then they will be even closer. If I take 100 measurements, it will be much closer. And how close this is measured by the fluctuations of these means that I'm calculating. And how exactly this becomes closer is measured by this standard deviation squared, or by the variance. And it tells you that the mean squared becomes smaller when you make more measurements by a factor 1 over n. So if I calculate now the standard deviation of this thing here, x1 plus xn divided by n, which I call the bracket of x, then I see that this is standard deviation of x, so this typical width divided by square of n. So this width here, the fluctuations that you will still have in this random variable will become smaller and smaller as 1 over square root of n, proportional to times the sigma of the original distribution. So that tells you, if you want to get a good estimate of the average, then you should take a lot of measurements. And this formula tells you how many measurements do you need roughly to get a certain accuracy of the measurement, right? So this will be a typical error that you make. And if you tell yourself, well, I need to know my result up to 10 to minus 3, this helps you estimating how many measurements do you need to make in order to get this accuracy. And that's a very simple thing, but it's very important, for example, when you do numerical simulations and you have noise in your data and you want to reduce this noise by simulating longer and longer and more, then this helps you estimating how much longer you have to work. Well, just a little example maybe. Take a dice, so there the xi are just 1, 2, 3, 4, 5, 6. What is the expectation value of xi? What is the expectation value of this x? So p of xi is equal 1/6. Now each number is equiprobable. So what is the expectation value again? Yes, please. Everybody votes for some value? Yes, 21 over 6. It's just over here. It's 3.5. You don't need to calculate, no? Okay. Sometimes it's good to not calculate and think. Okay, so what is the variance? Well, okay, you could calculate that. The variance itself is not so telling. It's much better to look at the standard deviation, which is the square root of the variance, right? So what would you estimate this to be? So let me plot this probability distribution. So this is I guess I 1, 2, 3, 4, 5, 6 p of, well, x equals I. So you have 1/6 here, 1/6 here, 1/6 here, 1/6 here. So you want to describe that by giving its average, which is here, and some kind of fluctuation. So what do you think comes out if you make this? Square root of 6. Why square root of 6? No, I mean you have to calculate that. So that the actual calculation is you sum over I 1/6 of I squared, right, that is this term, and then you subtract the square of, of the average that we already calculated, 3.5 squared. Okay, so if you want to do that, doesn't take too long, but you can do that, and that gives 35 over 12, if I'm not mistaken. Okay, and here you want to take the square root of, and that is roughly 1.7. Okay, so let's see, 1.7, that is about from here to here. So that is a typical standard deviation. See, that looks pretty reasonable. So if you tell me a dice has this average and this standard deviation, I have already an idea of what this dice is actually doing, even if I don't know this probability distribution in such a detail. No? And now what our calculation over here tells us is, now, so suppose that you suspect that this is actually not the real distribution of the dice, but somehow it has a mean that is shifted towards bigger values because somebody wants to cheat you. And so you want to check what is the mean value of your real dice, which maybe has not this probability distribution, but something else. No? Now, what this tells you is that if I want to know, say, up to 0.1, what is the real mean of my dice? How many times do I have to throw the dice in order to be relatively sure that I know this mean up to 0.1? So let's see. So I want to make a measurement with my dice. So real average of x, which maybe has not this distribution but something else, and I want it to up to precision, say 0.1. No. So how many times should I actually throw the dice? 100? Why 100? No, but now let's be a bit more precise. So I want, what does it mean, precision 0.1? I want that I know this x bar up to fluctuations which are of this order. So I want that the sigma of this x bar is roughly of the order of 0.1. No? Now this, actually not of x bar, which is the true average, but I want the scatter of my possible measurement to be not bigger than 0.1. So I'm going to calculate something like this. I throw the dice n times, I take the average. I ask that the fluctuations of such an average, when I do this many times even, that these fluctuations are not bigger than that, so that I know that what I will get from this procedure is within 0.1 from the true average. No? Okay, so this is what I want. Now here we calculated what this is, namely this is supposedly the true sigma of x divided by square root of n. Okay. Now, of course, if this is a very bad dice, you have no idea what the sigma of x is either. But if it's a dice that is just slightly skewed, you can, of course, estimate that to be the one of a perfect dice. So let's say this is presumably about 1.7 over square root of n. Okay. Now, if you want this to be 0.1, then what should I take for n? Yeah, so n bigger than 17 squared, which is about, well, which is 289, is about 300. Okay. So what if I want precision 0.01? How many more times should I think? 30,000, yes. So what is the sum rule? If I want 10 times more precision, I have to take 100 times more measurements, right? Because the error that I'm making goes down only like a square root, right? So if I want to gain one decimal here, I have to add 2 decimals here, in the other sense, right? Yeah? Okay. The question is, what is the difference between this notation and x bar? Okay, that's very important that this is very clear. So this has not the meaning of a true average over a probability distribution. This is just the definition of a random variable. So this means I look at the random variable, which is the sum of n independent samplings of a given random variable divided by n. So this is itself a random variable, the whole object. No, this is random. Okay, and we are asking about the distribution of this random variable. So each of these things has the same distribution by our assumption, and we call that P of x, which means so each P of xi is equal to P of xj is equal to some P of x. Okay. Now this distribution has a well-defined average and a well-defined variance, and that is what I call x bar. So this is by definition, for example, x P of x dx. No. So this is a number. This is not a random variable. This is a random variable. So if I write sigma of this object, what I mean is the square root of the variance of that random of that random variable. Yeah, right. Which we express through the variance of each random variable that enters into the definition of this thing. Is it clear? No? Okay, so this message should really arrive at everybody. This is extremely important. Arrives to you every day. If you work numerically, when you do statistical mechanics, you will see this coming up all the time. So this is very important. And once again, the message is, if you want to estimate an average better and better, you take more and more measurements. The accuracy goes like 1 over the square root of the number of measurements that you made. And once you know that, say, with 100 drawings, I get such and such accuracy, then you know what you will get when you do 10,000 drawings, 10,000 samplings. Then you get a factor of 10 more in accuracy. So if you know that really, and if you take it seriously, then you can plan your work really well. Say, then you know, is it possible to get a certain accuracy, or is it completely hopeless because I need billions of measurements, and so on and so forth. So this is not just playing around. This is very much of practical importance. Okay. So how are we actually? Okay. Just a quick reminder. You saw Gaussian distributions and Poisson distributions and so on. Can you quickly remind me of what are the means and the averages, the means and the variances of a Gaussian and of a... So what is P of x of a Gaussian? So there's a 2 pi here, and there is a sigma squared under the square root, e to minus x squared, maybe x minus x bar over, right. So sigma has the same units as x. So if there's a square here, there must be a square here. For this to be a probability distribution, it should have units of 1 over x in units. You know, if this is a length, for example, it should be in meters. So it should be 1 over meter here. So you can remember that very easily. So here, the variance will be the expectation value of this variable is what we already denoted like that. So this is x of p of x dx. And the variance is sigma squared, right? And for the Poissonian, do you all, so what is a Poissonian distribution actually? When does this arise? Hmm?
When the probability goes to 1 over a, 1 over some constant over a. As we increase the number of trivials, then the probability goes down to 0.
If you start from what? So once again from the start.
Okay. If we make the scale very small, then we
But which scale of what?
you have some constants, and then the probability goes like 1 over a, the number of
Let me give you, so I see that you have somehow a formal picture in your mind, but does somebody know processes which are described by Poisson distribution? Radioactivity, yes, very good. So, do you know why? I think in the last class you saw the Poissonian distribution. So why is radioactivity described by Poisson distribution? Or first, what is Poisson distribution in radioactivity? Can you tell me?
Poisson distribution. The formula for radioactivity or what?
No, so you say Poissonian distribution is associated, for example, with radioactivity. So can you be more precise? What does that mean?
How I understand Poisson distribution is if I have this sample, so if I have some intervals in each interval, if I take smaller and smaller intervals, I suppose decreases.
Yeah, okay. So what he's saying is more or less a route towards the truth. But so you get the Poissonian distribution if you have very rare processes. So you have, for example, a lot of radioactive atoms, right, which can decay, but each atom has a very small probability to decay, right? Now you ask, if I have 10,000 atoms and each one decays with a probability of 10 to minus 5 within a certain time interval, right? Then on average, I only expect 1/10 of the atoms, 1/10 of an atom to decay. Okay, let's take 10 to the 6 atoms, okay, and let's assume that each one has a probability of 10 to minus 5 to decay. Is the probability to decay within a certain time interval, whatever 0 and tau, whatever tau is. No, this would have to be much smaller than the lifetime of that material, so that you get the small probability. Okay. So now I ask, within this time interval, how many decays do I see? Okay. So n would be the number of decays observed. Okay. So on average, you expect 10 to the 6 times 10 to minus 5, no? So So you expect the average will be just 10, no? Right? So this is actually, this gives you a binomial distribution. You have so many events. Each event takes place with a probability which is extremely small. The average is n times p, no? So this is p, this is n, right? And that is what you call alpha for cases where this is extremely small and this is extremely large, such that the product is not huge, no? So now if you are in this situation, what you derived last time is that you get that P of n is Poisson distributed with parameter alpha. So that goes like, I think something like this, no? Alpha to the n over n factorial, I think. Is that right, no? Yeah, looks correct. Okay. So, yeah, once again, Poisson comes about if you have very rare processes with a lot of events, such that the average is finite and not infinite. Okay. A Gaussian comes about. When does a Gaussian come about? Do you know? Well, that's what we are discussing this time and next time. Usually you get Gaussians when you take large sums of variables. So if I take it's raining outside, I look at a small patch of soil and I count the raindrops that go into this patch, and I look at another patch. This is a random variable, how many raindrops I will see. No, the raindrops are not very rare, so we are not in this limit. So there are many raindrops. Then I ask, how is this number of raindrops per unit of time distributed over these patches? What I will see is a Gaussian distribution. Okay, that's the other limit that you were discussing last time. So if you have a large number of things that happen and you sum over many independent events, independent raindrops that come, for example, then you get the Gaussian. If you have very few events, such that on average you get just a finite number but not something very big, then you get the Poissonian distribution. Okay?
So, how much small is this time scale?
Well, so this has to be, for radioactivity, for example, this has to be much smaller than the lifetime. So this has to be such that this probability is very small. If you wait too long, no, then everything will decay, and then this probability will be big, and then you are not at all in this limit where this works well. So the time interval has to be small as compared to a typical time where something happens. So you have to describe rare processes. So Poisson distribution also comes about if you have classical particles that you are letting flow through a tube, for example, and then you ask how many particles per unit of time come out of this tube. So I have a flow here of particles, and they go out here, and then I count, say, within 1 second, how many particles do I see? Such a thing is typically Poisson distributed. Especially if these particles are very small and they don't see each other, they act independently, but I have a small number of particles that comes out, then typically the number in a unit in a given time will be Poisson distributed with a parameter that goes is proportional to tau, actually. So alpha goes like tau. Okay. That this is the case we'll describe next time, I guess. Okay. So I think it's important for you to have a feeling of when do you get Poisson and when do you get Gaussian and so on. What is, you know, the physical content of that, not just formula. Good. So this was a little bit of an aside. Now I want to discuss how you can estimate not only the average of your, say, the velocity distribution of gas particles, but you would also want to know what is the scatter, no, the distribution, the size of the distribution. So you have your Maxwell distribution, something like this. And I don't only want to know this value, I also want to know what is the variance, no? So how would you do that? If you proceed the same way as for computing this average, what would you do if you wanted to experimentally measure this width of the distribution? What would you do? So you would want so wanted is an estimate. You don't know your probability distribution, but you want to characterize it. And so you want an estimate for the sigma of x, or for the variance. So how do you do that? Well, you know that sigma squared of x is just defined as this, no? So why not just compute x average as we did before, and also x squared average more or less as we did before? No? That would be the natural thing to do, no? So so in other words, you could say, well, let me look at the following thing. I make n measurements of velocities, for example. I get xi for the velocity. And I compute also the average of my xi's. That is what we called bracket x before. And I square that. And I take the average of that. And that should be a good estimate for this, no? Sounds plausible, no? So here x is again defined by the average of the sampled values. So this goes from 1 to n. Okay, so I take n measurements. I calculate this object. I calculate the fluctuations around the mean of the sampled values. So this gives me, if I take 10 values, no, then I get one value here, a few here, and then something like this. I calculate the average of those, and I calculate the scatter of those around. And that should give me an idea of this thing. Okay? Now we will see that this is not exactly the best estimate of this. And that's something a little less trivial than what we did before. So let's compute the expectation value of this S, which is supposedly an estimate of this. You haven't seen that before, no? This calculation. Good. Okay. So let's write that out. So this will be 1 over n sum over I. Now let me take the square. So this is xi squared from this term squared, and I have to average that. And then there will be minus 1 over n is still here. Okay, so minus 2 times, then I have a sum over I to n xi times this thing here, right? And then plus I guess, n times just x squared, and here I have always to average, no? Okay, so I just multiply this out. Now let me write this as sum over j equals 1 to n xj, 1 over n, and here also. Yeah. Okay, now we have to do the average. So, and actually here it's better if I write it as two sums, like this. No? Is that clear? I write just x twice as a factor like this with two different indices. Okay. Now what we need is the following. So I assume xi and xj to be independent, right? That means the following, that if I take the average of the product, it's equal to xi times xj if for I non-equal to j. Of course, if I is equal to j, then this is not the same. Okay, now we evaluate this sum. So what do I get here? Here I get n times the average of x squared. Okay. Now here, what do I get? I get minus 2 times 1 over n from here. Okay, now I have a sum over I and j of the average of xi and xj. Okay, now this average I should split into I equals to j and I not equals to j. If I is equal to j, I have n such terms. Okay, so this is the term from I equals to j. N such terms, and I get the average of xi squared. And then I have n times n minus 1 pairs where I is not equal to j. And for those, I get just x average squared, no? From this here, which is x squared. Is that clear? Okay, then this term, this is n times 1 over n, 1 over n. So this is 1 over n. And then again, I have an average over such a sum of xj, xk averaged. And that gives again n times an x squared average plus n times n minus 1 x average squared. Okay. So, there's an overall thing like that. Okay, now we take terms together. Actually, I see that this term is the same as this term, but there's a 2 here. So I can just drop this term and put the minus 1 here. Okay. And what do we see? We can also cancel this 1 over n with this here. And what we get out is a very simple formula, but not quite trivial. If you see here, the x squared here comes with the n minus 1, and the x average squared comes also with an n minus 1. The whole thing is multiplied by 1 over n. So we get n minus 1 over n times x squared average minus x average squared. Okay, so, and what is that? That is nothing else than n minus 1 over n times the variance of x. Okay, so there's a kind of spectacular result that if we do this measurement here with n randomly sampled values from this distribution, we calculate this object that we think might be a good estimator of this variance if we look at the expectation value of what we are actually calculating. So what will we get on average? We see that we don't quite get the sigma squared. Let me write this as sigma squared. We don't quite get sigma squared, but almost, only almost, no? So we get sigma squared of x minus 1 over n sigma squared of x. So if we want to really be good estimators, of course, if n is very large, then this doesn't really matter. and you can forget about it. But if n is not so large, then you can make a systematic error by not correcting for that. So if you want your measurement to be a really unbiased, so-called unbiased estimate for this variance, then you better correct for the thing that we found. Namely, you would better define sigma estimate as 1 over n minus 1 times this sum. So xi minus x squared. So this is a good estimator for the true variance, namely because if we calculate this, the expectation value of this quantity, well, it's just this is just n times n minus 1, the expectation value of s. So this is just n times n minus 1 s, right? And that we just calculated to have this value. So the expectation value of this estimator here is the true variance. Okay. So this is a so-called unbiased estimator. So this random variable is an estimator for something, and it's unbiased because its expectation value gives you the right thing that you want to compute. If you do it this way, which is the naive way, you have an estimator, but it systematically underestimates the real fluctuations. The reason that you underestimate when you do like this is that if you have a certain tendency for your, say, 10 measurements to be on this side, okay, then you think the average is more on this side, and then you calculate the scatter with respect to that average, which is in the middle of this distribution. But the true average is actually a bit displaced. And so what you calculate is a smaller scatter because your average goes with the tendency of these values, and that gives you a smaller value than the true fluctuation. Okay. Yes.
What exactly is
S
S?
is a random variable, which is the result of your n measurements. So you take n values of a velocity, for example, no? You calculate this thing, you calculate that value out of n variables that you drew. So S is itself random because it's the result of a random process, no? So this is a random variable. Which has a certain distribution, but we are actually interested in its expectation value. So we calculate this random variable in order to get an estimate of this characteristic of the distribution of these things. And what I want to show you is what is the right way of defining this variable so that you get the best estimate of this. So if you want to characterize this random variable more, then you would not only have to calculate its expectation value, but also its fluctuations and so on. But that's not what we are interested in. So this takes the same role as this is an estimator for this characteristic. This thing was an estimator for the average for the other characteristic of this distribution. So now what you have learned is that if you don't know a distribution and you want to characterize its average and its variance by doing measurements, what you do is the following. You take n measurements, you calculate this object, and you calculate not this object, but that object here, right? And that gives you good estimates for these two characteristics. Okay. So that's the conclusion, no? So get estimates for the unknown, right? Unknown x bar and or expectation value of x and sigma square of x, which is the same as v of x, by computing these two formula, right? From n independently sampled variables. Okay. So this is at the basics of all statistical analysis, that how to estimate averages and fluctuations, and that's important. So the subtlety is in particular important if you make samplings with small n. So for example, you have a complicated experiment, you can only do the experiment 3 times. If you put here 3 instead of 2, then you underestimate your error quite significantly. So that's sometimes quite important. But of course, if you sample 1,000 times, then whether you take 1,000 or 999 is not really of any importance. Okay. Oh. Well. Okay, not here. Okay, fine. Sorry. Good. So, oh my God. So let me tell you about the law of large numbers now, which basically is it's a very simple statement, and we shouldn't spend much time on it. That just tells you that whatever is your distribution, if you measure enough times, then you will get a good estimate for the average. Okay, and this is very easy to prove, and sometimes people refer to it as the law of large numbers. Okay, so you can ask yourself, is it guaranteed that you will find, so can one find x bar as precisely as you want? By taking, as many measurements as you want. I mean, your gut feeling will be yes, of course, no. But so, since we do some theoretical physics here, let's also sort of prove that, no. So, okay, the answer is yes, of course, right? But let's see. Okay, so let's again consider our estimator of the average, no? This thing. So what we showed is that the sigma of this x average is equal to sigma of x divided by square root of n, right? Okay, now there's a very simple theorem that you can prove, and that goes under the name of Bien-Aimé-Chebyshev inequality. I mean, the complicated name doesn't justify the importance of the theorem. This is an extremely simple thing, namely, so remember that the average, the expectation value of this x is just x average, right? That's what we repeated in the beginning. So if you ask what is the probability that what you estimate by your measurement is different from the true average x bar by less than some number t times the standard deviation, this, okay, then this probability must be larger than 1 minus 1 over t squared. Okay, so what is the statement of this thing? It tells you that the probability that you're very close to the average is almost 1. So the larger you make this distance, the larger fluctuations you still allow, the smaller is the distance to 1. So the more likely you're going to hit this interval, no? So now, since this sigma x, when n becomes large, since this tends to 0 when n goes to infinity, then you see that the probability of coming within 1 over square root of n of the true average is essentially 1. No. So indeed, this theorem is guaranteeing you that when you take n large enough, then your estimator will, with probability 1 minus epsilon, be extremely close to the real average. No? And so this is the mathematical answer to this question. Do you understand? It's a very simple statement, but it's maybe a bit difficult to translate mathematics into meaning. Do you want me to say it again? Hmm? Can I? Read this? This? Bien-aimé Chebyshev inequality. So, bien-aimé. It's really not important. I never used this theorem after having learned it in high school. So, bien-aimé, N-A-Y-M-E, and this is T-C-H-E-B-Y, Chef, C-H-E-F-F. Okay. You better just remember what is behind this, which is extremely simple. So let me quickly give you the idea of how you prove that. Well, the proof is essentially trivial. You can say, okay, the
Question.
Yes.
Okay. When you talk about average and expectation value,
Mm-hmm.
are you not talking about the same thing?
Yes, I'm talking about the same thing. Yeah.
Okay, because here when you write, okay, previously you said no, they are okay. You say that when you write x like this, you mean it's a random
Yes.
variable.
Right. Okay.
Then you write x with a bar on top.
Mm-hmm.
Like in
Yes.
this case.
Mm-hmm.
Okay, in this case you say this is the expectation
Value.
value.
Yes.
So expectation value and average are different things.
Okay. So when I say expectation value, then I certainly always mean that I have a distribution. So then it means that I have a random variable x, and I have a distribution of this variable, and I sum over all the possibilities. And that is what I call expectation value. Okay? So there is no other meaning to that. But if I say average, of course, sloppily, you can call that also average. But people in everyday language call, of course, such an object an average of these numbers. No? so maybe I call this average and this expectation value. But sometimes people will also refer to an expectation value as saying this is the average of the random variable. But if you want to be clear, then you should maybe always call this expectation value. So the expectation value of this average is the expectation value of any of these variables coming in here. So the average of random numbers, average defined like sum divided by number of terms, is itself a random variable and has an expectation value and a variance and so on. Right. Okay, so let me now quickly give you the idea of what is behind this. This is very simple. So the variance of whatever quantity you're looking at, which is by definition the same thing as this here, this is you take your variable, you subtract its expectation value, you square that, and you take the expectation value of that. So this is for sure bigger than the probability that this object here inside is bigger than, say, here I put whatever I like, which is this object. So times the value of this deviation. Okay. So this is certainly bigger than the probability that this is bigger than this object here times the value of this object. No, that's very tricky. This is always positive. So if I take the expectation value of something positive, it is certainly bigger than if I take just those values where this is bigger than something. No? That's extremely something simple. So now you see that here you have t squared sigma squared x, right? Now you have sigma squared x is bigger equal to sigma x squared times something. And now you divide by sigma x squared, and you get 1 is bigger than this p times t squared. Right? Okay. So the probability that we wrote here is the 1 minus the probability here, because here it's smaller, here it's bigger. So the probability that this x minus x bar absolute value, say, squared is smaller than t sigma x squared, or you can also take away the square, is equal to 1 minus this p here. Okay, and that is, of course, bigger than now what do I want to no, sorry. Okay, this is the probability in the theorem, and we have the inequality that 1 minus this probability of the theorem, that this is smaller than 1, and then you take the t squared over here, and then you see that the p in the theorem, which is this guy here, must be bigger or equal. If you take it now over here and the t squared over there, then you get that this is bigger than 1 over t squared. Okay. And all that is just to prove mathematically rigorously, but almost without much physical meaning, that that the probability that you will land within a certain number times the standard deviation is nearly 1 with a small correction, which goes like 1 over this number here squared. So if you take this to be 10, then you have 99% probability at least that you will be within 10 standard deviations from the mean. And if the standard deviation goes to 0, when you make n large, then you're sure to come closer and closer to your average. Okay, so this makes you sure that if you want to sample an average, if you take enough measurements, you will come as close as you want. Okay, that's called the law of large numbers.
Is C a free parameter?
C, T?
T, yeah.
Yes, right. So for all t's, this is valid. Positive, of course. And I should say this inequality is extremely a weak inequality. For example, if you know what is this probability distribution already, if you know this is a Gaussian or so, then you don't need this inequality. Then you just calculate this thing, and you get a much better value than this estimate, which is based on this very stupid bound. No, so don't take this theorem too seriously. It just makes you sure that if you want to achieve precision, it's always possible. This is really not so important. What? Huh? Well, you know what I suggest to you? You try to prove that theorem for yourself, because it's very simple, and by thinking how you would prove it, you will understand something more about it. And if you don't manage, then you can ask Friday. Okay. Good. So, can we actually do 2 hours or? Yeah. Okay. So now we want to have more precise information of info about sums of many random variables. Okay, so far we sort of said what can we say if we sample n times a random variable and we calculate its average. We sum them up, we divide by the number, and we say that comes close to the real expectation value. We saw how you can estimate the standard deviation, but now we want to come close to this notion that when you take a lot of random variables and you take their sum, then very often, almost always, you get a Gaussian distribution for the sum. Okay, and that's known as the central limit theorem, and that's an extremely important thing to know. It's kind of basic, but it's very important. Okay, and you all already saw this coming up in the case of the binomial distribution, right? So, what is the object we are looking at? Call something again S, but here it's now just the sum of random variables, xi. So the xi do not necessarily have to be identically distributed here. So these are just independent random variables. They are independent but not necessarily identical. So now I'm not saying that this has to be every time the speed of a gas particle. It can be something once this, once that. Okay. So this is maybe an abstract thing. So what we want to know is what is the probability distribution of such a sum. And now you ask me, why should I care about this? But this is something that comes up extremely often. So let me give you a few examples so you understand what is the significance of that. Okay, for example, in thermodynamics, now if you calculate the energy of a body, or the magnetization, or all quantities that we call extensive, no? All quantities that are proportional to the volume, these are essentially sums of contributions from small subsystems, no? From many small subsystems. You know, your body is not fully correlated. Everything that happens here is correlated with what happens here. The energy of the full body is somehow a sum of small parts of energy that sum up, no? So, so if you write, for example, the total energy, you can sort of say this is like a sum over small subsystems, no? And you have energy contributions from the subsystems. So this is a typical example where you look at the quantity, which is a sum of many contributions, no? That happens essentially everywhere in thermodynamics or in statistical physics. So energy is an example, magnetization, specific heat, etc., etc. No? So, and now you would like to understand what happens with a quantity like that, which is a sum of many subsystems. So another example, which is extremely important, is random walks or Brownian motion. So do you see what could be? Do you know what the random walk is? No. So a random walk is something very simple. Take just one dimension. So you have a person standing here, and every unit of time, the person decides to either go to the right or to the left with a certain probability. Say with p, the person goes to the right. With 1 minus p equals q, it goes to the left, and then something like this is happening. So you can also look at this as a drunken person walking around. Okay. That is, of course, what happens with molecules. If you put a large molecule into a liquid, for example, this liquid is kicked by smaller. The large molecule is kicked by the smaller molecules of the liquid all the time, and somehow it is making random motion like this. Of course, in 3 dimensions, and the step size can be different. Here it's just step size 1 all the time, and these probabilities are the same. In a liquid that may fluctuate, may be a bit more complicated, but Brownian motion is essentially also random walk. Okay? And now what you want to ask is, after a long time, where is my particle? Of course, it's not somewhere precise. It will be, there will be a probability distribution where your particle will be, no? Because all these kicks are random. You don't know in advance whether it will go to the left or to the right. So there's a probability distribution. And the position in this one-dimensional case, what is the position? The position is just the sum of individual steps, no? +1 or -1, and I sum that up over many steps. That gives something like this, no? So for random walks, the position after a long time, after many steps, is just a sum over individual steps. And now you want to know what is the distribution of this position? How does it look actually? And that can even be measured if you take several big molecules and you put them into a liquid, and you put them together originally in some spot like this, and now each of these molecules is independently doing this Brownian motion, this random walk. Afterwards, you look where have all these particles gone, and they will sample this probability distribution very well, no? And so you can even do an experiment and measure this probability distribution just by looking how many particles are now at this and that position. That gives you a very good estimate of this probability distribution. So does somebody know how such a liquid, a drop of heavier molecules is behaving in a liquid what is happen on the Brownian motion when I start? So I start with a drop in a liquid and I let it evolve. Do you know what happens? What is going to happen with the density profile of this? So this will somehow expand now. Do you know what the shape is of this?
Like a wave going outward, like putting in the water.
Yeah. Right. So now I look from this side and so I start with something like this. No, I put everything at the beginning, say, just in one dimension, and now. So I put 100 particles here, big particles, and now they get each of them gets random kicks. So some particles go here, some go here with these probabilities, 1/2 over there, 1/2 over there, and so on. So this will spread, no? Does something like this. Do you know the precise shape of how this will look? Diffracted? No, but there's no wave mechanics here. No. Yes, just Gaussian, and actually, indeed. So that's the important point. It will look Gaussian, but why? So can you actually have already all the material to tell me that this must be a Gaussian. Do you realize that?
Initially it was localized at some point, and as time goes on, it gets.
Well, it will become broader. That is sort of obvious, but why is it exactly a Gaussian and not a Lorentzian or whatever?
Because we have equal probability for each degrees of freedom.
Yeah, you sort of refer to this central limit theorem, which we are going to derive. But think of last class where I guess Marco told you about the binomial distribution and what it does in the limit of large numbers of samples, no? So you had a P and a Q, no? That's the probability for the variable. So you had the binomial distribution, no? The binomial. So P was the probability that X was 1, I guess, and Q, which is just 1 minus P, is the probability that was that X is 0, no? Okay, and what did you prove about this? That if you take n variables like that, and then you ask how many ones do I have, then you found that that is a binomial distribution, and when the number n is big, then what?
In times log n, which is e raised to approximates
Yeah, and the Gaussian, so okay, so when n goes to infinity, this goes to the p of the sum over these x i's goes to becomes Gaussian, okay, and what are the characteristics of this Gaussian? What is the mean and what is the variance? Huh? No. What is the mean of this Gaussian? N times p, that's the expectation value of this sum, right? So that's sum over x. And what is the variance? Yeah. Yeah. Okay. Okay, so what is the relation between what you discussed there, this binomial distribution, and this problem? Do you see that?
So as it makes a large number of steps,
Mm-hmm.
because like Gaussian as we saw.
Right, but now precise translation between this problem and this problem. So in this problem, with probability p, I go to the right. With probability 1 minus p, I go to the left. So what is exactly the relation between what you calculated here and what we want to know here? How can we make a matching between this?
It's a binomial. I can take P to be the probability of H, Q, say, as I make a large number of trials, we say the mean is NP, and the mean is NP. So here,
Yeah, okay. So I want to make a really precise translation between this problem, which is sort of a stylized problem, stripped of all details, just the skeleton of the essence, and this here, which has a bit more, decoration. It's still very stylized. So, but you see here we have x equals 1, x equals 0, no? But here we have step plus 1 or step minus 1, no? So if we want to make a connection, we have to shift this, we have to say that here the position, right, is equal to the number, the sum of all steps xi, or let me call it maybe yi, and yi is either plus 1 with probability p, and yi being minus 1 has probability 1 minus p. Okay, now I'm asking what is the distribution of the position. Here we were asking about the distribution of a sum of ones or zeros. No? So what is the connection? Well, that's not so difficult. Let me say this is equal to n plus sum over I of yi, minus n and yi plus 1. Okay? We just added and subtracted n. Okay? Now this object here is either 0 or 2, no? Okay? So let me then divide this by 2 and multiply by 2. Now this guy here is either 0 or 1, no? And now it's exactly this problem, right? So now if you know how this is distributed, right, then you just take it times 2 and you subtract n. That means just that you're shrinking your Gaussian by a factor of 2 and you displace it by something, but you, of course, still have a Gaussian, right? So what you did here, this work here, immediately translates here, and you could immediately tell me that if I take a large number of steps and I look at the overall shape, I will see a Gaussian with essentially the same variance, maybe divided by or multiplied by factor 2 squared, and the mean is is going to be shifted. The mean should be n times p. That's the average number of steps to the right, and then minus n times 1 minus p. That's the average of steps to the left. So this is n times 2p minus 1. This is the average position. No? Or expectation value of the position. Okay. Good. Right. Okay. So so you see here we have two examples which are very generic, where you have an observable like the energy or the magnetization or the position, which are sums of many independent contributions, and it looks like that very often you get a Gaussian distribution of the outcome. Okay, and now we want to understand how this comes about. On one hand, on the other hand, I want to show you now what is special actually about the Gaussian distribution and what is maybe behind the fact that you tend always to these Gaussians. And next time we will prove that using some nice technique, which is generating functions. But for today, I just want to give you an intuition about Gaussian distributions and their properties. And then next time we'll see that in more detail. Okay, so properties of Gaussians, and I want to give you an intuitive understanding of why you get Gaussians out all the time. Okay, and that you can get by calculating moments of this observable. Okay, so this is the observable that we want to look at. For example, the position. Now, so we want to know what is the distribution of P of S. Well, how can we characterize the distribution? We can characterize it by calculating the moments. You know what moments are? That are expectation values of powers of this observable, no? And under quite general conditions, if you know all the moments, you actually, the distribution is uniquely defined, unless these moments are diverging too fast or so. But so it's a general technique if you want to find a distribution and you know how to calculate the moments, then you can actually often derive what is the distribution just by knowing all these moments. Okay, now let's understand how moments of such a big sum behave in the leading order in n. So when n is large, what dominates most these moments? Okay, and let me simplify to that case where the expectation value of all these x is 0, so they have 0 mean, and they have just fluctuations. Okay. Of course, you can always shift by the mean so as to achieve that. Then, okay. Now, so what I want to calculate is this thing. So this is by definition this I equals 1 to n xi to the power of m averaged. And that I can also write like this. I take m copies of this sum and I sum over these m copies and I just multiply that out. Do you see that? So I just write this m times with different indices and then I multiply it out. Okay, and then I have to average, right? Okay, so what can we say about this sum? Let's discuss the case where there's an even number of where m is when m is odd, then there will at least be one index here that is not equal to the others because they're just an odd number, so then you cannot pair up. No, let me. No, sorry. That's not quite true. If you take m equals 1, then there is just one term here, and you get 0 because you average. You just compute this thing, right? and by assumption, this is 0. Now, when m is equal to 2, what happens? Then you have I1 and I2, xi1, xi2. Okay. Now, if the variables are independent, yes, so I assume independent variables again. So then this is only non-zero if I1 is equal to I2, right? So this will be the same sum delta I1, I2 of xi1 squared average, right? And that gives me sum over I1, xi1 squared averaged. And if they are identically distributed, so if they are identical, then I get x squared average times n. Okay? So these are the first two moments, and that's essentially the same thing as we did before, just in the simpler case where the average is already, and the expectation value is already 0. Now what happens when I take m equals 3? Yeah. So what happens? If all the indices are different, then I get average of x times average of x times average of x, and that's 0 by assumption, no? So if two are the same and one is different, what do I get? So when say I1 is equal to I2 but is not equal to I3, then this thing here will give x1 xi1 squared times xi3, no? But that's also 0 because this is, by assumption, this is 0, no? So the only term that will be non-zero is when all the indices are equal, right? Okay, so this is going to be sum over I1 of xi1 cubed average, which is n times x cubed expectation value, sorry, if you have identical variables. Okay. Now let's discuss the case m equals 4, and then you will see the pattern. Okay, so and this is a very useful exercise, which usually I give us the first exercise in the graduate diploma, because it gives you a really good feeling of what happens with these sums. Okay, so if I take here an average, then let's understand which combinations of indices give you non-zero results. So what do I have to have? I cannot have an index that is not equal to another one, because then that index is can be taken out independently under this product, and then it is killed to be 0 by this. No? So all indices have to come together with other indices and be equal. So how can I do this? 2 and 2, for example, right? For example, this, or I can do this, or this, or what else? All of them equal. Can I do 3 and something? No, because then there's only one left, and that's not possible. So I can also do this, no? Now, that's instructive to understand what will happen. So each of these three terms, this and this one and this one and this one, gives me an x squared times x squared, right? So I have 3 times this, and then I have to sum over all the possibilities of having different indices here and here. How many such possibilities are there? How many possibilities do I have to choose an index here which is different from an index here? Well, for this index I can choose whatever, that gives n, no? And for this index it has to be different from that one, that then I have n minus 1 choices, no? Good, okay. So I get 3x squared average squared times n minus 1. Now what about this term? This term gives me all the x are equal, so it's x to the 4 averaged. And how many choices for the indices do I have? Just n, no? Okay, now what you see is the following, that this term here goes essentially like n squared to the leading order, no? This term goes only like n, and when n is large, we will just essentially neglect that, no? So for m equals 4, we can say this tends to go to 3x squared times n squared, and then the rest is subdominant, right? If you look at the second order term here, it goes like n times x squared. So you see, there's a similarity between here and here. It's n goes with, for each factor of x squared, you get the factor of n. If you look at the third order term, there's only a factor of n, like here, with the third power here, but there is not an n to the 3 halves. You see, so here you have n, then you have n squared, but the third moment goes also like n, and not like a higher power of n, and that essentially indicates that this is a subleading term. If you see here that the natural scaling variable, the natural object to occur is something like this. So for each x squared, you get the factor of n. Here you see that for x, you don't get a factor of square root of n like you get here, but you get something less. So this will also be subleading when you take large n. So if you redefine your variable as, say, let's call that x tilde, then this will be, so this will be 3 times x tilde squared average, right? And this will be 1 times x tilde squared average. But this here will be x tilde cubed average, but 1 over square root of n in front, if you make this change of variables. And if you concentrate on the distribution of x tilde, and you want x tilde to be of order 1, that is your variable of interest, then you see that this is going to be subdominant. Okay, and now we'll finish in 3 minutes. Now you can go on calculating these moments in this fashion, right? So for m equals 5, you will again see that you get something subdominant, because the fifth guy you cannot really pair. You have it to associate with one of the pairs. So this will go like n squared again. But for m equals 6, you will find it goes like n to the 3. And if you're brave, then you will check for yourself that you get this form here, times 5 times 3 times 1, etc. If you have m equals 2 times n, then you get n to the n times x squared to the n times 2n minus 1 times 3 times 1. So you can check that just doing this combinatorics one step further, you see that the dominant term always comes from pairing just two variables. Then you ask how many choices do I have to do that. Essentially, you have n to the number of pairs choices to make. Each pair gives you an x squared. And then you have to ask how many ways do I have to pair up m variables, no? And the number of pairings is this. Okay. Okay. Now, what does this tell me? That tells me that. Okay. Now we have calculated. So this gives us these moments s to the m for all m, no, in leading order for m even. Okay. And now you can check for yourself that these precise factors you have here. So if you're now asking what is the distribution for S, that this is going to be, these moments are the same as if you have a Gaussian distribution. So let me see. These are the same moments as for a Gaussian distribution, like this, with sigma is equal to n times x squared. Okay. So the variance of this Gaussian should, of course, be the variance of this sum. The variance of the sum, as we derived in the beginning, is the sum of the variances. So this will be n times the variance of a single variable, right? And what you can check now for yourself is just by computing moments of this distribution, that these moments are exactly the same as those that we calculated in this kind of pedestrian physicist's way, right? So this gives you a very good feel of how it comes that a Gaussian is coming out, because you get the same moments, and you see what you're sort of neglecting. You're neglecting these subdominant terms, etc. So next time we will rederive that in a much more mathematical, rigorous way. But I think this is a very instructive way of approaching the problem. And I will make more comments about the phenomenon that we saw here, about these pairings. And I will also rederive that in more rigorous terms. Okay, and then we'll stop here